Okay, here's a walkthrough of slide 133, and the idea here is we want to understand how a predicate like odd x actually generates a series of alternative results. So we start off here with this query, odd x. We have our four-port model here corresponding to this query, and first thing that happens is we enter the call port of the goal, and Prolog starts then searching the database for a clause whose head will unify with odd x, and it finds one right away with odd 1. So that's going to unify, or it's going to instantiate x to 1, and we're going to get an exit to the user. So let me go ahead and write x equals 1 here. Then we get an exit, and the user is going to see x equals 1. User doesn't like it. They hit semicolon. That sends us in the redo port, uninstantiates x. I'm just going to scratch out the value, and then Prolog starts looking for another clause that unifies with odd x. It finds one here. Now we have a rule, odd n. So I'm going to move this pointer for this goal into the database to the second clause for odd. And now from slide 90, we know that when we have a variable and a goal and a variable using the head of a rule, we get unification between those. So I'm going to connect these two up in this way to show that x and n are unified. Anything that happens to n in this body is going to happen to x at the top level. Okay, so we start along here, and we're going to shift to the ports over here, and we see that the first thing it does is odd m. And so now we have a goal, and it's going to start looking in the database, and each goal has its own pointer. So we're going to imagine, so we're going to represent that by pointing down to a different, or to another copy of these clauses for odd. So we find that odd 1 unifies with odd m. So that's going to give us m equals 1 here. We're going to exit to the next goal. N is m plus 1. That's going to give us n equals 3. And now we exit. And essentially, when we exit this recursive call, we end up exiting out of odd. So since n is 3 and n is unified with x in this goal, we get a unification here of x and 3, and the user sees that. They would have typed a semicolon, I should have shown that. Next thing they'll see is x equals 3. But of course they don't like it, and they hit semicolon. We go in the redo, and then we come, so the redo here forces us in the redo here in this first call, and then we backtrack. So we uninstantiate n equals 3, we go back here to this goal, odd m, we uninstantiate m, and then Prolog says, well, okay, is there another clause for odd that can work? It starts searching, and sure enough, it finds another one right here. So let's adjust the pointer, and now we're here. And now this clause starts running. So it says, okay, odd m, and then that's going to start this goal, looking for clauses to unify with odd m, and again it's got its own pointer, so all these goals have pointers into the clauses. It's just one copy of the clauses, but I'm showing multiple copies here to hopefully make it clear that each goal points to or can point to a different place. So we have odd m, that's going to instantiate m to 1. We exit here, then we say n is m plus 2, so that's going to give us n equals 3. We exit here, and that produces an exit up here And then now, so we're right here, and I should have drawn this sooner, but we have unification between m here and n here. And so when I unify n with 3 over here, because n is unified with m, this now gives me another value up here for m. Now this m becomes 3, it's unified with the n in this call, and then we can move forward again. So now we say n is m plus 2, m's 3, that makes n 5. We exit here, this instantiates x to 5 up here, the user sees x equals 5. Again, they type semicolon, and the process continues. Let's go through one more round of it. So we get pushed in redo here, which pushes us in redo here, which pushes us in redo here. So we uninstantiate 3, we backtrack, we uninstantiate m, and now Prolog says, okay, are there clauses that can further satisfy odd? It says, well, yeah, there's another clause here. So we advance the pointer for this goal in the database, and we start the whole process again. But let's go ahead and work through it. So we have odd 1, or sorry, here we have odd m. It's going to be here. It's going to unify m with 1. We exit. This n becomes 3. And again, I forgot to emphasize that we have this unification between these. So we have n equals 3. We have unification between n and m here. So now this goal can instantiate m to 3. It's going to exit calling this goal, and now that gives us n is 3 plus 2, or 5. And then that exits, which essentially does what? Now I'm stuck. So exits here, and we end up I'm stuck. I'm going to pause for a second and then continue. Let me see if I can save this. So we got n equals 3 here. We exit. N is 5 here. And what I didn't draw, now that I see, was that we had uninstantiation here. So with this n equals 5 here, we have a new value. So we have n equals 5. N and m are unified, and now m up here becomes 5. We can move forward again. We've got n is m plus 2. That's 7. We exit here, and that gives us another value, again by this n being unified with this x in the top level goal. We now see that x equals 7. We go back to the user, or at this point, the user sees another value, x equals 7, and this process will just go on infinitely. So the key things to recognize here is this unification between this variable in a goal and the same variable in the head of a rule. And then notice as we look at this, we see different values for m and n in each of these calls. At the call that's now at the bottom level, m is 1, n is 3. At the next level up, it's m is 3, n is 5. And we just see this pattern repeating as we go down. And remember that it's slide 90 that has this key rule about this unification. All right, that's it. Sorry about that stall in the middle, but maybe that'll help you understand what's happening when, or how Prolog generates, or how a predicate like odd can generate a number of alternatives.